This instruction is on the test to determine the fatigue or endurance limit for a steel specimen. The method that we'll use is called the rotating beam method, where the specimen experiences a pure bending condition and is caused to rotate continuously. In order to get the numerical value for that fatigue limit, we need to develop an SN plot. S stands for stress, and N stands for the number of cycles that sample failed with that amount of stress on it. And that will allow you to develop data points to develop this plot. This would be the amount of stress, and this would be the number of cycles that occurred for that sample to fail. The idea is that there is some minimum amount of stress that the sample will not fail, and so that's called the stress limit or the fatigue, the endurance limit or the fatigue limit. Now, in order to do this in the lab, we need to, first of all, produce a pure bending condition with lab equipment and know the number of cycles for that pure bending condition and calculate the amount of stress. Let's first talk about the amount of stress. The equipment is called a fatigue tester, and the way it works is the specimen is here. In order to put it in pure bending, there's a simple support over here. You can start to see the beam condition being developed. There's a simple support at each end. This is rigid up to the collet. This is rigid up to the collet, so that's a beam, and the specimen completes the beam. Now, in order to put it in pure bending, there's a pan down here, and we put weight on that pan. And this yoke and turnbuckle allows the amount of weight on that pan to be evenly split. And if you keep these at right angles, then you have a beam bending condition where that specimen is in pure bending. There's a motor back here that rotates this whole thing. So now we have developed the rotating beam pure bending condition that will allow us to calculate the amount of stress. Now, in order to calculate that amount of stress, we need to know, here's the amount of stress that would be produced. It's the amount of moment divided by the section modulus now that's for the specimen that's being bent. The section modulus is determined by the diameter of the specimen, and the amount of moment is determined by the total amount of weight, and that weight is made up of two things. One is the weight that you put on the pan, and then something called the tear weight. That tear weight is the amount of weight that is the simulated weight that would be applied to the sample. If there's no weight on this pan, then notice that these parts of the machine would actually cause it to be in bending due to the tear weight. Those will be given to you. That tear weight will be given to you. The amount of weight on the pan will be determined by your loading condition. And the lever arm is a property of the machine. So now that you know the amount of moment and you know the section modulus, you can calculate the amount of stress, and that would be on this axis of your plot. The number of cycles, you'll be given the RPMs of the motor, and you will have an hour timer. It can't be reset. So what you'll need to do when you run this experiment is you'll need to record the value on this hour timer, and the last two decimals, the last two digits are hundredths of an hour, so you need to be careful to record it with the decimal values. So you'll need to you'll need to record it at the beginning of the test, and then the equipment will stop. When the sample fails, it will automatically stop, and so then you'll go into the lab and record it, the hours on this meter at the end of the test. So that will allow you to know enough information to plot data points, and they will definitely scatter And what you do in Excel is create a trend line. You put all the data points on there, and you create a trend line, and you print out, you have Excel tell you the equation for that trend line. And what you need to do, we probably will not run these samples the 20 days that would allow us to claim that it has run until we have the amount of stress that it will never fail. So what we're going to do is we're going to run it some number of hours and days and plot all of this data, and then the trend line can be extrapolated to 5 times 10 to the 7th cycles. That is the amount of cycles that we claim that amount of stress will essentially never fail with that amount of stress. So that's called the endurance or the fatigue limit. That amount of stress is called the endurance or the fatigue limit. And you will compare that to a published value for the endurance or fatigue limit. Real quickly, let's just talk about the parts of the machine and how you'll set it up. There's a nut and a rubber collet in here. This is called the tailstock. You'll slide this tailstock back in order to get the sample, in order to just physically fit it in there. Here's a weight hanger. This little hanger here will allow you to take the weight off the sample while you're loading it in a hook. And then as you start to time the sample, you'll release that hook and write down the recording on the hour meter, which is sitting right up here, as the start time. What you'll do in order to load that sample is take the collets out, put it on the specimen, and then fit them back into the machine as a unit. This hook is engaged in order so that you can load it without any weight on it. And notice too that this has to be perpendicular in order for the statics to work. In order for this to be in pure bending, this yoke has to be perpendicular to the beam.